Something is wrong with the early universe. When NASA launched the James Webb Space Telescope, it was supposed to show us the first galaxies slowly forming, gently, out of gas and dust in the calm moments after the Big Bang. Instead, in the deepest fields it can see, it keeps finding tiny red dots. Point-like objects, just a few pixels across, sitting at distances that place them less than 1 billion years after the beginning of everything. And when we measure their masses, they should not exist. They are called little red dots. In 2023, when the first deep JWST survey data came back, the team looked for the faint blue clumps of early star formation the models had predicted. They found some, but mixed in with them was something no one expected. A population of extremely compact, extremely red objects, appearing across nearly every field JWST examined. The red color meant they were either heavily obscured by dust or they were doing something else entirely. The point-like shape meant that whatever was inside them was extremely small and extremely bright. And when the follow-up spectra came back, they showed a signature that changes what these dots could possibly be. To understand why the dots are strange, you have to understand what the universe should look like at the redshifts where they appear. Redshift is how astronomers measure cosmic distance and cosmic age. The further away something is, the more the expansion of space has stretched the light coming from it, and the redder that light gets when it reaches us. A redshift of 1 means the light has been traveling for roughly 8 billion years. A redshift of 10 means the light left when the universe was only about 400 million years old. Most of the little red dots sit at redshifts between 4 and 8, meaning we are seeing them as they were between 600 million and 1.6 billion years after the Big Bang. In the standard model, the first stars form around 100 million years after the Big Bang. Some of those stars die and leave behind black holes. Those small black holes fall together, merge, and slowly grow by pulling in gas. Growth is limited by the Eddington limit, the rate at which radiation streaming off a black hole starts pushing away the gas trying to fall in. Under this standard picture, growing a supermassive black hole takes time, a lot of time. The little red dots do not have that time. When astronomers took spectra of the brightest ones, they found broad emission lines, the fingerprint of gas moving at thousands of kilometers per second around something extremely dense. That signature is how you identify an active galactic nucleus, an accreting supermassive black hole. From the width of those lines in standard scaling relations, the black hole masses came out at 10 million to 1 billion solar masses. 10 million solar masses at redshift 8 means a black hole with the mass of a small galaxy, existing less than 700 million years after the Big Bang. That is not enough time to grow from a stellar mass seed at the Eddington limit, not even close. And the strangeness gets worse. In our local universe, supermassive black holes track the mass of their host galaxies, roughly 1 part in 1,000 of the total stellar mass. The little red dots break that relationship. Some appear to be tens of % black hole by mass. In a few cases, the black hole seems to weigh more than everything else in the object combined, as if a supermassive black hole formed first, and only a small envelope of stars gathered around it afterward. That is a complete inversion of the usual picture, where galaxies form first and grow black holes at their centers slowly over billions of years. If those numbers are right, the early universe was building supermassive black holes before it built the galaxies to hold them. 3 explanations are being explored. The first is direct collapse. In this picture, some of the earliest gas clouds in the universe were massive enough and cool enough to collapse into a black hole directly without ever forming stars. That would produce a heavy seed, 10,000 to 100,000 solar masses on day 1, instead of the small stellar mass seed the standard model assumes. Heavy seeds have a head start on growth and could reach the little red dot mass range in the time available. The problem is that direct collapse requires specific and delicate conditions, and it is not clear the early universe provided them at the required rate. The second explanation is that the growth limit itself is wrong. If early black holes could accrete at rates well above the standard Eddington limit, they could grow much faster than the models predict. There are theoretical mechanisms for the super-Eddington accretion, but they are hard to sustain over the long timescales required. The third possibility is the least comfortable, that the mass estimates are wrong. If the broad emission lines are being produced by outflowing gas rather than orbiting gas, or if the geometry of the emitting region is different from what we assume, the black hole masses could drop by a factor of 10 or more. The dots would still be strange, just not as impossible. JWST is still looking. Each new deep field it examines produces more little red dots, and each new spectrum sharpens the picture. Some of the dots turn out to be less extreme than the first candidates suggested. Others hold up under scrutiny. The population is real. Whether it points to a new pathway for black hole formation, a broken assumption in cosmology, or a systematic error in how we measure high redshift masses, that is what the next few years of observations will decide. What we can say now is that the earliest visible universe is producing objects our models did not predict. Something is out there, glowing red at the edge of the observable universe. And whatever it is, it got there faster than physics said it should. If you like this one, hit subscribe. There's more strangeness where this came from.